Okay, let's dive right into this explainer and tackle our big essential question for today. How exactly do humans and robots coordinate through controls? Now, if you've been working through Grade 7 robotics, specifically Unit 04, you know we spend a lot of time focusing on manual control, event handling, and user input. But honestly, there's a massive bridge between the code you write on your screen, the controller in your hand, and the actual physical machine sitting on the table. Today, we're going to look strictly at the hardware side of that equation. We're going to break down exactly how your physical build choices completely dictate your success in remote control and coordination.
Right off the bat, we need to talk about a massive myth that so many people believe when they first get into robotics. And that myth is that any working build is equally good for remote control. It is so incredibly easy to fall into this trap. You put some wheels on a chassis, slap on a couple of basic motors, sync up your controller, push the joystick forward, and boom, the robot moves. Absolute success, right? Well, not exactly. Because just because a robot can physically roll forward doesn't mean it has the actual usability or reliability required to complete a specific task. We really have to separate the simple idea of moving from the much more complex idea of controlled movement.
Think about it like this. Imagine you're trying to drive a car with a blindfold on. I mean, sure, the engine works perfectly fine, but that doesn't mean you can actually control the vehicle, right? If you can't see the road, you can't react. You can't process any feedback from your environment. And that exact same logic applies to our robots. If we don't build them with the right types of motors or the right placement of sensors, our ability to manually control them just completely plummets. Instead of smoothly guiding the machine, you literally end up fighting it every step of the way.
So what this really boils down to is coordination. Successful remote control is entirely about coordination, and that requires a direct, solid connection between your physical build choices and your real-world performance testing. Coordination isn't just some fancy buzzword here. It's the ultimate goal of Unit 04. It means that you, the human, provide some user input, the robot handles that event, takes a physical action, gathers feedback from the environment, and then gives you the opportunity to adjust. It's a continuous loop. And if your physical build is clunky, well, that seamless loop is totally broken.
This brings us to a really harsh reality of hardware design. Motors built purely for speed often fail miserably at manual control, whereas motors built for tiny incremental movements are the ones that succeed. Now, when you first start performance testing, there's always this huge temptation to just use the fastest motors available. I get it, speed is fun. But if you are trying to map your joystick controls to a really precise behavior, like say picking up a super delicate object or navigating through a very narrow gap, a motor that only knows how to sprint is going to overshoot the target every single time. It literally lacks the mechanical ability to listen to subtle user inputs.
To achieve true responsiveness during a task, your robot desperately needs the mechanical ability to make frequent, tiny corrections based on your input. In fact, if you take away just one golden rule today, let it be this. Coordination relies on frequent, small adjustments. Manual control is pretty much never a straight line. It's a constant, ongoing conversation between you and the machine. You push the joystick slightly left to dodge a barrier, then slightly right to center the robot back up. If your build choices don't physically allow for those frequent, micro-adjustments, your robot is going to fail its performance tests, and it honestly won't matter how flawless your programming is.
To really see how these physical choices play out in the real world, let's set up a head-to-head showdown between two completely different robot designs. We've talked a lot about motors, but now we really need to look at sensing and feedback, which is the other massive component of Unit 04. We're going to put these two different physical builds to the test to see which one actually enables real human-robot coordination.
In one corner, we have Build A, which is designed to only sense what is directly in front of it. And in the other corner, we have Build B, which gathers feedback from multiple directions simultaneously. Think about how these physical design choices fundamentally change event handling. Build A can definitely tell you if you're about to crash head-on into a wall. That is absolutely helpful, but it's also incredibly limited. Build B, on the other hand, is constantly pulling in data from the front, the left, and the right. It's generating this incredibly rich field of feedback that you, the remote control operator, can use to make split-second decisions.
Spoiler alert, Build B is the clear winner for remote coordination. Trying to drive Build A is essentially like trying to navigate your way through a crowded room while looking through a paper towel tube. You just don't have the whole picture. You desperately need that side sensor feedback to map your controls to the robot's behavior effectively. With better peripheral feedback, it is vastly easier to prevent side collisions during manual control. Because the robot is handling events from multiple sides at once, it empowers you to have a much quicker response to user input.
And that drastically improves the overall usability and reliability of the machine. The build literally dictates the success of the remote control.
Okay, so let's put all of this into a practical scenario. Imagine you're entering a performance testing phase, and your robot's objective is to maneuver through a really complex maze. You've got to navigate some seriously tight corners without getting stuck. You have to react quickly to dead ends, which means backing up and rotating with absolute precision. And above all, you have to maintain constant human-robot feedback to ensure you aren't just scraping along the walls the entire time.
So, knowing everything we now know about the importance of sensor placement and incremental motors, I want you to step into the role of the lead engineer. What specific build modification would you propose to conquer this maze task? Would you swap out high-speed motors for ones capable of fine, incremental movement? Would you add more sensors to handle the event of blindly approaching a tight corner? Remember, the entire goal of Unit 04 is seamlessly mapping your controls to the robot's behavior. So take a hard look at your current build, think about the harsh demands of the maze, and ask yourself, what is the one physical change that will give you the ultimate remote control?